Okay, we are going to hear next talk from Sergey Shevchenko, Kharkiv National University, and as but mainly from Kharkiv National University, yes. And talk is styled non-diabatic Landau-Zener-Stückelberg-Majorana transition, dynamics, and interference. Very interesting. So please, Sergey.
Thank you. I know that you are interested. The main part of my talk will be about non-adiabatic transitions. But let me start from introducing myself. I'm mostly from Verkin Institute for Low Temperature Physics and Engineering. And these are my students from the institute who contributed in this work. And we collaborate with Franco Nori from RIKEN. In the institute, I'm head of Department of Superconducting and Mesoscopic Structures, of which I'll tell a few words, given that we are speaking about quantum research in Europe and in Ukraine, and also about speaking about education. I'm a part-time professor in Kharkiv National University, where I delivered lectures to the fifth year students in theoretical physics, and the lecture notes were published in the World Scientific, and I'll tell in this slide about this book, Mesoscopic Physics Meets Quantum Engineering. The contents starts from the introduction of what is quantum engineering, then the chapter devoted to quantum computations, the other one about quantum mechanics of qubits, and I'll partly tell about this now. Superconducting quantum circuits, normal quantum circuits, namely like quantum dots, and about hybrid quantum structures, like what is known as circuit quantum electrodynamics. So this is the lecture course developed for one semester. Now, I'd like to tell you in 3 slides about our department, where we study related systems, mesoscopic scale, nanoscopic scale ones, like qubits, metamaterials, superlattices, single-photon detectors. And before I start the main subject of my talk, in 2 slides, I'll show you what my colleague in our department do concerning metamaterials and superconducting single-photon detectors. Several years ago, a collaboration between University of Geneva ID Quantique and Corning Incorporation resulted in demonstration of quantum key distribution over record, at that time 400 kilometers. This became possible partly due to single-photon detectors used in those experiments, which were made of, importantly, superconducting ultra-thin films of molybdenum silicium. And these are the illustration of the detectors developed in our institute. Superconducting quantum metamaterials. If atoms make conventional material, then we know that atoms are natural elements which are practically not controllable. In contrast, metamaterial is composed of meta-atoms. These are artificially prepared elements in the form of microcircuits, and these are easily controllable. Here's the example, the array of magnetically coupled RF circuits with Josephson junctions. And this is the meta surface formed of the squids. And this is visualized, this is the visualization of electromagnetic excitations. And now, going back to the main part of my talk, educational part will be to tell you about the diversity of two-level systems. Then, what are these transitions? Monadiabatic Landau-Zener-Stückelberg-Majorana transitions. Then I'll tell how, in a little bit more details, how these are described by the least probably known approach following Majorana. I'll show you what is now known as the LZSM interferometry, and one of the topics in quantum control by means of these non-adiabatic transitions, LZSM logic gates. So let me start by saying you that very many different systems behave as qubits, which are driven by external signals. Just look how diverse they are. We theorists describe this by the state vector in the superpositional state of two basic states and the Hamiltonian. Hamiltonian, the pseudo-spin one in terms of Pauli matrices. Here delta, look at this energy diagram, is the minimal distance between the ground and excited energy, and epsilon is the driving parameter, the parameter which changes the energy distance. If such system is driven here and there, it experiences transitions. And these are important for the characterization of the system and for its control. So just 2 slides about qubits. These can be very diverse, but in 2 groups we can split. Microscopic ones, like ions, photons, of which we've heard a lot today, yesterday, and spins. And larger ones, like mesoscopic and even macroscopic ones. These employ electronic states in quantum dots, charge or phase degree of freedom in superconducting structures, etc. I'll spend 2 slides for 2 examples. First, a spin qubit. This can be, for example, an electron spin. If it is forward, the constant magnetic field can be used to make it polarized in one of the 2 directions. If we further apply alternating magnetic field, it would flip it, and thus quantum logical gates, for instance, from 0 to 1, this is an X logical gate, can be implemented. In reality, of course, these are somewhat more complicated. Here's an example. The spin qubit is based on an impurity in a field effect transistor. Another example, Josephson qubits. These are based on Josephson effect. And one of the Josephson effects, non-stationary one, was firstly directly observed in our institute. Well, and here's an example what superconducting qubits are. This is a ring with several Josephson junctions pierced by magnetic flux, and these describe 2 basic states for which low temperatures are needed. And this is one of the examples, 2 coupled qubits controlled by DC and AC signals, and the readout. And maybe the main part of my talk the key message of my talk is what are the Landau-Zener-Stückelberg-Majorana transitions. These were studied many years ago by these four scientists, that time under 30, from 4 different countries, and the papers were written the same year in different languages. They studied transitions in a two-level system, in a qubit, as we would say today. The problem can, in its simplest form, can be formulated. Let us start in the ground state to the left, and being driven, what would be the excitation probability after passing this avoided level crossing? This can be done repeatedly with the frequency omega and the period t. And then the transition probability after single transition is described by the probability by very simple formula. So these scientists, they obtained this very quite simple formula. Probability is exponential of including delta, which is the adiabaticity parameter. In the numerator, delta, the minimal splitting. In the denominator, velocity at which the avoided level crossing is passed. This is the controlling epsilon parameter over t derivative. So if this adiabaticity parameter is large, then this is 0, and the system stays in the ground state, which is needed, say, for adiabatic quantum computation, of which we've heard. So in the adiabatic quantum computation, you'd better have this large. If it is not very large, then with certain probability we are excited, and going backward, the interference with the acquired Stückelberg phase results in the quantum fringes. Before I show you the fringes and the dynamics, a few more words about these original papers. Some of you know about the Landau-Zener formula, and maybe most of you know about this as a Landau-Zener and maybe Stückelberg formula. It is quite rarely when people refer to Majorana work in this context. But in fact, it was published even earlier, and given its depth, this work, given that it's underestimated, we spent on this quite efforts, and I'll tell you about this. Look, interestingly, even among Landau's papers, this paper is his second top-cited paper, etc. So, because of what I said, I would like to spend to Majorana's approach 3 slides. We solved the Schrödinger equation for the wave function with the amplitudes alpha and beta, and with this Hamiltonian. After Majorana's substitutions, we obtain second-order differential equations. These are solved by the direct and inverse Laplace transformation. To get the answer from the inverse Laplace transform, we need to use the steepest descent method. And for this, we use this integration circuit. These are quite details. And then we obtain for the wave, for the state vector, for its components, alpha and beta, such lengthy expressions, which I visualize here. Look, for this very simple system, for 1 qubit, for a 2-level system, being driven by a linear signal, not exact, by the asymptotic solution, looks quite complicated. This is visualized here, the probability staying in the ground state as a function of time. We compare exact solution by Zener in terms of parabolic cylinder functions and Majorana's solution, which you partly can see here. Importantly, if we go to the details, we can start not from the ground state like Majorana, we can go beyond Majorana's approximation. We can start from any superpositional state. These are details, but what's important is that from Majorana's approach, we can get a quite known adiabatic impulse model. In this slide, I would like to tell you what is it, which is important for very different problems in quantum control including. Look again, our two-level system, and we start to the left. We would like to know the excitation probability to the right. These can be solved separating dynamics in 3 stages, so that the final vector state is obtained from the initial one by multiplying it by 3 matrices. Firstly, adiabatic evolution. Then, in the very narrow, in fact, in calculations, we can safely assume this in one point, impulse type transition, probability to be excited, and then adiabatic evolution again. So that's the essence of the adiabatic impulse model. The continuous dynamics can be very nicely, very conveniently approximated by the solution of 3 matrices. This I advertised that we prepared this for publication. And this is the visualization. Upper level qubit occupation versus time in units of 1 period if the system is driven periodically from left to right and further. Single passage Landau-Zener excitation with the probability given by the formula which I've shown you. And after the second time the energy levels meet, like in the Mach-Zehnder interferometer, the resulting occupation probability can be either 0, can be either reduced if the interference is destructive, or excited in the constructive fashion. If we do this during many periods, the constructive interference results in the full transition to the upper excited state and backward. These are Rabi-like oscillations. Importantly, if we can we can describe and obtain such dynamics, these with the repetitive passages of the avoided level crossing, this can be used to control the state of quantum systems. And this is the visualization, destructive interference after the second passage of the avoided level crossing, and constructive interference, where we obtain full excitation probability. And this, under these resonant conditions, we obtain resonances, which in fact can also be explained as multi-photon resonances, where distance between energy levels is matched by the integer number of excited photons. This is the picture of an excited state occupation probability with the multi-photon resonances along these lines. This can be used to describe systems for the spectroscopy. For the power calibration from the Stuckelberg oscillations between these spots, And more detailed analysis can of the shape of these resonances can result, for instance, their width can help us to extract relaxation parameters. This is how we interrelate with the experiment and thus demonstrate that such interferograms can be useful to describe how a system evolves from its ground state into any desirable superposition state, allowing control and manipulation of individual quantum systems. Finally, I would like to give you one more illustration of what else can be done with the LZSM transitions. These are quantum gates. In general, these are most commonly, these are realized with Rabi oscillations. But also, alternatively, these can be realized with the non-adiabatic transitions. For example, in this slide, I would like to show you how to realize X or NOT gate via two LZSM consequent transitions under the condition of constructive interference. Look, Rabi oscillations. A two-level system is driven by the periodical signal with small amplitude and with the frequency equal to the resonant one. This is the visualization of its dynamics on the Bloch sphere, where starting from the North Pole, we end up after many periods of the driving signal in the South Pole, the NOT gate. And this is the dynamics shown in Bloch coordinates as a function of time. We can see that the Z component of the Bloch vector starts from 1 and ends in -1 after many periods of excitation. Alternatively, as I said, we can do this in the LZSM approach, which was realized recently experimentally. Again, periodical signal, but now the amplitude is quite large. In this illustration, we take the parameters with the probability equal to 1/2. Again, starting from one state, we end up with the other one. And this is done firstly differently, and secondly on a shorter time scale. Which brings me to the next slide, to the last slide, the conclusions. What I wanted to tell you is that the LZSM formula is quite simple, but we continue to study this evergreen problem, and in particular, we study how to derive it and how to develop it following Majorana's approach. The quantum interference in such processes allows to both control and characterize the state of a quantum system. And I wanted to tell you about the LZSM interferograms and one illustration of quantum control, LZSM logic gates. Thank you for your attention.
Thank you for interesting talk. It's very exciting that two-level system is неисчерпаемая как атом, да? Как it's so many results was obtained in previous time, especially in work of Nikolai Vitanov, and I have some interesting results. But as you can see, still it's possible to obtain very interesting and very nice results. So the talk is open for question. As I see in the chat, is this quantum gate preparation robust against control imperfections? Pavlo Pushkin.
As far as I understand, we are speaking about quantum gates, and these do have advantages over conventional ones, and one of the advantage is its robustness against some of the imperfections. For example, what is needed here is the precise frequency to get the resonant excitation, and with certain probability go to the other pole. And these calculations, these going from one pole to the other one, for instance, requires rotating wave approximation. Of course, the methods are quite developed, and the approximations are well studied, but this very different approach, as scrutinized here, and which we continue study in the paper, which is going to be prepared for publication. This is somewhat protected from certain imperfections in parameters. So it does.
Okay. Other question, please. Okay, then I would like to ask a more general question. Two-level system is very simple, and solution, numerical solution, gives the results very quickly. What is the reason for analytical results for this model, for this intermediate non-adiabatic state? Is it what you have additional from this results comparing with simple numerical simulation of the two-level system?
Speaking about the simplest non-simple problem of a driven two-level system, even these cannot be exactly solved. So the solutions of Landau-Zener-Stückelberg-Majorana, these are very different, and they solve the problem in different approaches. And they obtained asymptotic solutions, not the exact one, if we do not consider parabolic cylinder functions as exact ones. This also require numerics. Yes, numerically nowadays we can check and build this, but with the analytics we can obtain some parameters of the transition, some not only dynamics but some additional parameters. For example, following say Vitanov's paper, we can define the transition time, the time needed for one transition, for how long the transition lasts, and this time should be at least shorter than the decoherence time. Otherwise the coherent processes are destroyed. So analytical formulas allow us to write down such conditions with several parameters like adiabaticity parameter, time needed for the transition, etc.
Okay, so other questions? No questions, then we